last time, okay, so I've laid out the basic forces and the basic particles that we know about. And I talked about the nuclear force quite a bit last time. Now I'd like to talk briefly about the more exotic things we see in general in particle physics. I mean, a little bit of history of particle physics is people at the turn of the last century discovered alpha particles, alpha decay of heavy elements. They discovered X-rays, began to realize what, you know, and there was, people knew what atoms were, the charge of an electron, and basically the model that we have of the atom, which electrons circulate a nucleus, was sort of understood. Then a big breakthrough was the development of a machine that could take particles, protons, say, but also other single atoms, and accelerate them to high energies. Okay, and the basic idea was, it was called the most, you know, the first machines that did this were called? Cyclotron, right? And the basic idea was simply this idea that if you have a magnetic field into the board and a particle is moving like that, then you get a V cross B. Oh, let's make it out of the board. No, so that is out of the board. Yeah, dot's out of the board. Yeah, V cross B, so then it'll sit here in orbit. But then you need, that's not good enough. You can arrange an electric field, say in a top half and a bottom half, and as the particle's moving that way, and if it's charged, you can give it a kick. You can accelerate it. Anyway, that was in the 30s. A person named the name of Lawrence, who was out in Berkeley, sort of really pioneered this. And by the late 30s, there was a whole set of cyclotrons. If you go back into the 60s and the 70s, many particle physics, many physics departments had a cyclotron. There's an alternative thing called a Van de Graaff, which is a Van de Graaff generator, which is essentially a glorified way of getting static electricity. You get this huge voltage. You apply a big voltage to a charged particle, you can make it move. There was a Van de Graaff here, actually. I don't know when it was shut down, but in the past. So you start to accelerate particles to high energy. Now, what's kind of funny is when you say particle physics, it's synonymous with particle accelerators. You might say, well, I'm always worried about accelerators and smashing things into each other. Well, the answer is that's because that's the only way we can do it. I mean, it'd be quite interesting to build a plasma of particles at very high energy. I mean, realize when I say plasma, I mean a plasma is particles at high energy, like in the sun or in a flame. But those are at modestly high energy. The most recent accelerator, the one at CERN that turned on and then they had a huge accident, by the way. They had a huge explosion of liquid helium. No one was killed, but a big amount of damage. They're going to be down for a while. But that accelerator is taking single protons and taking them, this is embarrassing, I don't remember the exact number. I believe the energy they're targeting is something like 12 TeV. 10 to the 12th EV. All right? Remember, 1 GeV times c squared is E equals mc squared for a proton. Very roughly, 938 MeV, 0.938 GeV. This is the GeV is 10 to the 9. So this is basically taking each proton and giving it a gamma factor, 1,000. And if we actually did that for ordinary matter, and we had a macroscopic amount of it, that's way more energetic than the center of the sun. Okay? The center of the sun, your typical proton is heated up to keV. Okay? Million degrees Kelvin, effectively. This is much higher energies, and we can only do it to one particle at a time. I mean, it would be nice if we could build some machine that could make a whole box of it, and there would be other things to study. But we can't do that, so we're limited to just shooting individual particles at each other. And also, if we wouldn't understand what the particles do and what they're made out of, there's really no other thing to do except send individual particles at each other. But it's not that that's the only question that would be interesting, by any means. It's just the only one we can ask. Okay? So the study of particle physics is basically smashing atoms together, atom smashers. And protons are one thing. Basically, we've done protons and electrons. Although you can also do heavier nuclei. You do a whole nucleus. And in fact, then bigger is better. And so like they'll slash lead on lead or uranium on uranium. You know, two really, really heavy nuclei. The problem when you do that, you get basically such a mess that interpretation is very, very, very hard. When you smash uranium at very high energies, you get this just spray of bits of atom. You know, pions, which are two quarks, and protons and neutrons, and other more exotic combinations of quarks. Just as a reminder, we did this before. There's the down quark, the up quark, the strange quark, the charm quark, the bottom quark, the top quark. Each of these is a family. The family of normal matter has an electron and an electron neutrino. And then this quark family is associated with the muon and the mu neutrino. And that's associated with the tau and the tau neutrino. And those are sort of the basic particles. And the gamma, the photon, is the carrier of electricity and magnetism. The gluon carries the strong force. And the W and Z bosons, so these are not spin 1/2 particles. These are spin 1 particles. They carry the weak force. And there must be a graviton that would be spin 2 that I don't even write down. We haven't directly detected it. And that's the basic result of basically 50 years of experimentation where particles are smashed into each other. And just to give a rough sense of what happens, if you smash a proton into a proton, or a proton into an antiproton, those are made up of these up and down quarks, and they're antiquarks. And you basically get a bunch of interaction amongst these quarks. So in point of fact, at the LHC where they're doing this experiment, or 12 TeV, so here's a proton, it's got 3 quarks, and it comes at this incredible energy at another proton. Why are you laughing? Oh. Yeah. Oh no, Mr. Bill. In point of fact, what happens is that most of the time there's kind of a glancing reaction. And with this much spare energy, gamma of 1,000, essentially there's enough energy in this collision I could produce 1,000 protons. I mean, you could. You would have to produce them in a proton-antiproton pairs. Those sorts of interactions aren't so interesting. What's interesting is if the 2 quarks hit dead on, and then we get to see some interesting reaction between just 2 quarks. There's technically a harder to build type of accelerator where you accelerate an electron and an anti-electron. And that's a much cleaner reaction because you don't basically have these other quarks going along for the ride. If the 2 electrons hit, they can more readily produce a more interesting particle, and just a few of them. One of the big challenges is there's this huge detector, which is the size, well, one of them is the size of this, well, it's bigger than this room. And it sees all these spray of particles coming out, and you're trying to reconstruct what happened inside. As we saw in the weak decay, there are, the beta decay. There are certain rules about the reactions that can happen. And this is one of the really marvelous things. It's one thing just to draw this family of particles. There's these quarks and there's these leptons, and that's what there is. But what goes along with this is there's these wonderful mathematical properties which describe what type of reactions that can happen, what type of particles can be created. And I just have time to say that. I can't really, it's a whole field of study to start, to explain that further. But for instance, one of the types of particles you can make with quarks are, I mentioned this, 3 quarks make protons and neutrons, and those are stable. But there are particles that aren't stable made of like an up quark and a down quark alone, or combinations thereof. Those are called pions. And which quarks can be combined together to make which particles, or at which rate you'll create them if you have 2 quarks react, turns out there's this group, there's a wonderful model behind all of this that basically explains the rate of all possible interactions. And it's called the Standard Model of Particle Physics. So just beware, so that there's it's a big achievement that people have worked out. Essentially, all the interactions amongst these particles are tolerably well understood, up to energies that we can access. Once we smash things at higher and higher energies, we may see new stuff. We really hope we do. And the history of the field, I think I mentioned, is that this is higher and higher mass, is that basically you had to build bigger and bigger accelerators in order to create these highest energy things, because basically you're going to create them out of thin air, if you will, using the total energy available in the system, and that comes from your gamma. And gamma is basically your electricity bill at some level. And also just an incredible amount of serious equipment and well, it's very fine-tuned equipment, but also big, heavy, serious, big magnets, big power supply. This accelerator takes about as much energy as a small city. Okay? I mean, the way they run this accelerator is very much tied to how much power they can get out of the power grid, where they are there in Geneva, Switzerland. Right? Like, they can't run in the middle of the day when everyone wants their air conditioner on. Things like that. I'm not familiar with the details, but I know that the power available in that area is a big part of their running schedule, because that's how much energy it takes to run the thing. So what are a few of the sort of interesting things? Well, I mean, I've mentioned several times in this class, but let me repeat it, that for every particle, there's an antiparticle. And you can readily create, there's rules about what can happen, and one of them is that you can only certain reactions are allowed. A type of reaction that is definitely allowed is if this is, say, an electron and an anti-electron, they can annihilate into a photon, just like that. And the rules for this come out of a quantum mechanical calculation, which Richard Feynman realized could be written in a simple drawing way, and that there was a lot of meaning in these drawings. It turns out that simple reaction, to just have an electron and anti-electron disappear into a photon, it's allowed from the quantum mechanics, but it doesn't conserve energy momentum. If the photon bounces off of something else, then it can conserve energy momentum. Or maybe the photon can then create some other particle. For instance, it could create a proton and an antiproton, or sometimes written as P and P bar. I'll put the bar for the antiparticle. Or quark and an antiquark. Or some new particle, or some heavier particle, one of these heavier particles. A mu and a mu bar, muon and an anti-muon, or a tau and an anti-tau. And certain of these reactions involve the strong force, and certain of these reactions involve the weak force. The ones that involve the weak force are rarer. But then it turns out the strong force reactions never change family. These are called the families. Only the weak force reactions allow you to create this family out of particles from that family. And that's the way it is. So most of the reactions are going to be within a family, because the strong force, being stronger, has just a higher rate of reactions. Another way of phrasing that is if I collide two particles at each other and there's a variety of possible outcomes, the reactions which involve the stronger forces are much more likely. In some very vague sense, if the force is 1,000,000 times stronger, then I'm going to have 1,000,000 times more reactions which are based on that force than in a force that's 1,000,000 times weaker. So there's a whole class of particle physics where you're looking for these rare reactions that are due to the weak force, which amongst other things create particles of a different family. I think that's essentially all I want to say about particle physics. This has been a very sketchy introduction. I've been, invite you to look at the book, which has a pretty good sort of introduction to all this. Are there any questions? Yeah.
Have we noted any difference in mass between the different families of quarks?
Oh yeah, there's a huge difference. Absolutely huge. I didn't bring my particle data book today. The top quark weighs, I think, almost 200 GeV. GeV. These quarks weigh about 1/10 of a GeV. So it's like a factor of 1,000. An electron has a weight of 511 keV. Every time I say just an energy, then you're mentally supposed to multiply it by c squared. And strictly I should say MeV c squared, but we always just drop that off, okay? So whereas a proton has a weight of what, GeV, an electron has a weight of 1/2000th of that, okay? As you go up, muon is some number of MeV, hundreds of MeV. And the tau, I think it's a few GeV. I'm forgetting, okay? And I'm on film forgetting, but I'm forgetting. Okay, so there's definitely a very, very large mass. I mean, this is such a rich subject, but I think I'm just going to stop unless there's some other question, because I want to talk a little bit about cosmology. Okay. One of the really fascinating things, and this is a big subject of study in this department, and indeed nationwide, but this department was sort of early on the game, is sort of how this particle physics plays in to what we know about cosmology. And it turns out what particles there are that are available, what forces there are available, had a huge amount to do with why the universe is the way it is today. Let me just try to say a few words about the Big Bang. You may well know there was an astronomer by the name of Hubble who started studying the distance to galaxies. If you go back to like the 20s, there was a big debate. What are those fuzzy things in a telescope that you see? And then people realized, oh, wait a minute. That's a bunch of stars, and we're in one of them, right? So totally non-obvious, right? If you go look with your eyes, you can see one galaxy, right? Which is the Andromeda galaxy. I don't know if you know that. Or if you're in the southern hemisphere, there's two satellite galaxies to our galaxy, the Large Magellanic Cloud and the Small Magellanic Cloud. They're actually really big. I've never seen them. Actually, I went to the southern hemisphere and I forgot to look. I was there for 2 weeks. I can't believe it. But so I've never seen them. But they're quite big. Those are kind of almost in our galaxy's orbit. The next one that's a normal big galaxy is quite a ways away. It's 1 million light years away, whereas the galaxy is about 10,000 light years across. And you can just barely see it if someone, if you have a sky telescope friend, they can point it out. Probably not from Cleveland, but on like in mountains, you can barely see it. You can see it with the binoculars. All right. So people didn't even know that there were galaxies, then they finally figured out, oh, that is what's going on. There was a famous series of debates in the 20s, I believe it was. I may have the time scale a little off. And they realized, oh, those are these huge things, and we're in one. This fuzz, which is called the Milky Way, is actually the same sort of thing. And then it was Hubble who built a big telescope outside Los Angeles and measured. There's various ways you can tell the distance to galaxies, and that's a whole story in astronomy. How do I tell the distance to things? And I'm not even going to begin to try to explain it. But he roughly measured the distance to things. And the amazing thing he found was that if galaxies were far away from us, they appeared to be moving away from us, right? So here we are in draw an eye. That's a typical way astronomers like to illustrate something. And here's some galaxy out far away. The light from the galaxy, which can be seen because you can look at the spectrum of the stars. Remember, I've explained how the sun is this good black body. But not only a black body, right? If you have gas around the star or around the galaxy or dust, you get absorption lines, which without going into the details, we've talked about in this class. The fact is atoms have these energy levels, which is a quantum mechanical effect. So fundamentally, if you have a simple gas in a galaxy, you will see lines. They could either be glowing, or they could be lines where light is absorbed. Like, so you either can have gas with a bright object behind, and what will happen is right at the energies of transitions between atomic levels, the energy will be absorbed. And so you might see essentially something like the black body from a star, and then you'll see these missing, just these troughs in it. Those are from gas. Or if you excite the gas can glow, but it'll tend to glow with those lines where the electrons fell down from a higher energy level to lower energy level. And you can then find, you can notice that, and remarkably, even though these things are literally, the closest one is 1 billion light years away, which means it's 1 billion years old, the light we see from it, roughly, Andromeda. They're across the whole universe, we see exactly the same spectrum of light as we measure in apparatus here on Earth. Exactly the same spectrum of light. In fact, that's a whole field of study is to look really, really carefully. Precision measurements. Are the atoms in incredibly distant galaxies from right after the Big Bang, 12 billion light years away, 12 billion light year, 12 billion years old, are they the same type? Are the atoms behaving the same as what we have in a laboratory here on Earth? And to parts per million, at least, looking at details of all the atomic shells and such, they are remarkable. So you're seeing the same stuff, and then those lines give you they give you something to look at, and you get a Doppler shift. If this thing is running away from you, there's a red shift. Just like the Doppler shift of sound, there's one for light. I've mentioned it before. And what Hubble, so I've told you a lot. Coming back, bringing it back, what Hubble found was that whenever a galaxy was far away, it was moving away. And the further away it was, the faster it was moving. So it's just this very simple, basic ground rule of the universe. Depending on how far other galaxies are from us, they're moving away from us always. All of them are moving away from us. And the further out they are, the faster they're moving. And if you think about that a while, there's really only one kind of coherent explanation for it. It is the Big Bang. And I'm going to do a little model. Oh, here's good. This is hopefully not so dusty. I'm going to make a little model of the Big Bang. That's a model of the Big Bang. Okay? The model of the Big Bang is that I start with an eraser, and I just toss it up, and the gravity of the Earth slows it down, and then it finally turned over and came back. That turns out not our universe. It's not going to, the come back part isn't a good model. The good model of our universe is that I tossed it just hard enough that it barely escapes the field of the Earth, okay, and just keeps going and slows down at the end of the day. That's a pretty good model. Ignores dark energy. So why was that the same idea? How is that related to this? It was related in a very simple way. So suppose, for whatever reason, we don't know the reason. We don't know the reason. We don't understand why there was a Big Bang. We don't understand what happened before the Big Bang. It's not clear we could ever know such things. But suppose all the matter in some region is exploding. Okay? That's exactly the same as the toss I make, the original toss. The explosion is my hand giving it the kick. And it all starts moving apart. There's mutual gravity from all this stuff. And it's slowing it down. That's the slowing down of the chalk as it goes up, okay? And so if I wanted to do some really fancy experiment, and I put a little, Whoville on my hand, and the Whoville, they're going to measure the velocity of the chalk, okay? But we don't do it as one piece of chalk. There's a bunch of pieces of chalk that I tossed real rapidly. Clearly, the further away, the higher up the chalk is, the slower it's going. Right when it's leaving my hand, it's going fast. And the further away it is, the slower it's going. That's not exactly the same as here, but it's the basic idea is the same, just simply that gravity slowed it down. Here it's a little bit different because there's a time issue too. When you look at here, the further away is, the slower it's going. Here it's just quite a little bit different but it's the same idea, but a little bit different in the following sense. when I look far away, I am looking far away, but there's just this basic simple fact about light travel. Light travel takes time. So if I see something that's 1 billion light years away, I'm seeing light from 1 billion years ago. Oh, and I said something wrong. The closest galaxy is 1 million light years away. It's 1 million light years. I knew that was off. The edge of the universe is 12 billion light years away. So the furthest stars we see are about 10 billion years old, okay? The reason it's moving faster is simply because I'm measuring the point that was at the beginning of that, at the early time of my hand, okay, of me throwing the chalk. And since then, gravity has been slowing down the explosion. It's just been fighting against the explosion. And so the stuff that's nearby is not moving very fast, okay? And so that explanation sort of, well, and what's interesting is that Hubble's observation came within a period of time not too long after general relativity came out. Before general relativity, you probably wouldn't have known what to do with Hubble's observation, certainly not from a mathematical theory point of view. But Einstein had come out with this incredible creation, which was general relativity, which was a really compelling view of gravity, which really seemed to explain everything. It mixed up space and time and mass, and it had been proven right with real subtleties. Remember I talked about light bending around the sun? And in fact, it was a priest, Lemaitre, Belgian priest, who postulated that Einstein's theory, that he realized that one consequence of general relativity was a prediction that you could have had basically a Big Bang. And that was around the time that Hubble came out with his observation. And sort of everything fell into place. The realization that general relativity is the framework. It's not simple Newtonian gravity. Although most of the behavior of the Big Bang can be explained with actually a simple just Newton's gravity with a couple little extra things you have to stick in, which rigorously should be derived from general relativity. But it is just about as simple as the chalk going up and down. And the simple fact that that's what's going on. This is basically called the Hubble law. The further something is, the faster it is going away from us. And it's just simply a statement that we're looking back in time, and the earlier times were right after the explosion, and right after the explosion, the velocities were higher. And since then, everything has been slowing down. Okay? That's a basic view of the Big Bang. There's another idea in the Big Bang that people always, it's one of the obvious things you always wonder about. Well, where was the center of the Big Bang? And the answer, you guys know the answer? The answer is there was no center. Okay? So what does it mean that there was no center? Well, let me just explain how it can happen. Suppose in space here of this room, I draw a grid, a three-dimensional grid, like this. Right, as I start to fill it in, the sketch just gets unreadable, right? But let me just draw grid lines in all three, X, Y, Z. Let's say every grid is a foot apart. Let's just imaginary, just put them in. Imagine now I got the room filled with a grid. In fact, no, I don't fill the room with a grid, I fill all of space with a grid. Okay? Maybe we started constructing it here. Maybe it started getting constructed in Alpha Centauri. Who knows? Doesn't matter. Grids everywhere. And then I simply take the length between segments and I expand it, right? That is a type of expansion where if you're on any one node of that grid, all other points on the grid appear to be moving away from you. But there is no center, okay? And it's really just a mathematical consequence. That's the only way we can think of that's an expansion for everybody, but no one's special, okay? And we are fairly certain that must be what's going on. I mean, unless, for instance, unless you somehow think that the Earth is, the Earth is rotating about the sun, so it can't be centered on the Earth. Maybe somehow it's centered on the Milky Way, but that's really odd. I mean, especially given the fact that stuff that it's the visible edge of the universe, 12 billion light years away, the stars are, the atoms in the stars within a part per million have the exact same energy levels. And, they're the exact same hydrogen, the exact same helium as we see on Earth. Okay? Why would the Earth be different? So that's the view. It's just An infinite grid that's expanding. Which brings up the next question. Is the universe infinite? And, well, how do we know? How would we know? What can we know? There's a simple fact. I mean, if you just run the movie backwards, I forgot to make a connection. Let me make the connection, then ask the question again. The connection I wanted to make is, so everything is moving away from us, and the earlier you look, the faster it was going. If you think about running the movie backwards, earlier and earlier and earlier, things must have been closer and closer and closer. Because after all, if something is moving away from me for a long time, that means a long time ago it was closer to me. I mean, it has to be. So if you think about looking at the expansion now and just running the movie backwards, it must have been that everything was in one place, or very compact, not in one place. It was all crunched together. So there was, and that's the Big Bang. If you run this movie backwards, and it's taken 70 years to get the measurements right. The measurement has now been done. All these velocities have been carefully enough measured that you can ask the question, well, what was the start time for this explosion that we see? And the answer was, I think it's like 12.3 something billion years, plus or minus a few hundred million years. We really know with a really high precision exactly how long ago the initial explosion was. Okay? So that's the connection I forgot to make. Once you've seen this expansion, the only possibility is that there was, stuff was together and it started with a very dense hot plasma. But there was a time for that. And so the question was, is the universe infinite? That's what I was trying to answer. Well, there's a basic idea. Look, 12.3 billion years ago, everything we see was all crunched together in one little spot that then exploded. We can't see any stars or any galaxies that are older than 12.3 billion years because in the plasma, it was just a plasma. There were no stars yet. It was all sort of this uniform plasma of high energy particles, of all these things in a really angry state. Remember I said it would be really interesting if I could make a box of stuff at 1 TeV each particle, but I can't. But if I could, I'd get to study what it was like in the early Big Bang. That's what the early Big Bang was like. It was a plasma of hot particles, and almost certainly there was some earlier time it was higher energy particles. There were no stars, there were no galaxies to look at. So there's this idea of the horizon. The horizon is just simply the age of the universe, 12.3 billion light years, times the speed of light. That's the furthest away there is anything we can look at. Okay? There almost certainly is stuff further than that. So, the idea being, if I sit at one node on this grid that's expanding, and I look out 12 billion light years, I carve out a volume. In 12 billion more years, I'll be able to carve out a volume twice as big. But today, I can only look out 12 billion light years. And that's called our horizon, and that's the size of what we call our universe. And so we get to punt and not answer the question. Is the universe infinite? We don't know. Could we know? No, we can't. We can't see out there. It's not causally connected. If you want to look a trillion light years out, you got to wait a trillion years. And you can look a trillion light years out. Until a trillion years passes, we can't see stuff from out there. It's not causally connected to us. What is remarkable is that the universe is absolutely and utterly the same as best we can tell in all directions we look. So the entire universe that we can see, our horizon, it's 12 billion light years radius, 24 billion light years diameter. It looks utterly the same. This statement that the atoms look the same and they have the same line, colors, and spectra, to part in a million at least, all directions. It's about the same density of galaxies in all directions. And there's also one remarkable thing about the Big Bang is that from the Big Bang you would predict that there's a well, actually, it was predicted. There was a prediction in the 60s. A great physicist named Dickey at Princeton. Now, he didn't come up with it completely alone. It's also Gamow. They thought, it's like, well, the Big Bang, people recognize there must be some truth to this, but for a long time people thought, God, what are we ever really going to know? In fact, so I'm sort of in cosmology, that's my field. I remember my father has a a master's degree in physics. He'd gone to grad school back in the 60s for a few years. And when I told him I was going into cosmology, he kind of acted real funny for a couple of days. And then I realized back in those days, it was it was a field for flakes. Because they had these ideas, but the data was so poor that there was nothing numerical you could really do. And now what's remarkable is we know a huge amount. Anyway, one of the predictions that was made around that time was, gee, if there was such a big bang, at early times it was a plasma of all these particles. Okay? In fact, what was it? It was a black body spectrum of all those particles. And what do I mean by that? It's a hot plasma, and there's KT. That's a nice concept from this class, right? There's that the energy of stuff in thermal equilibrium is given by a Boltzmann distribution, where the probability that I have some energy E is given by this weighting. And so if the energy is around KT, the weighting is sort of e to the minus 1, which is 1 over 2.7, about 1 to 3. If the energy is 1,000 times KT, it's a third to the raised to the 1,000th power, which is negligible, right? So energies are comparable to KT. And if KT is bigger than mc squared for a particle, then you can create that particle and its antiparticle just spontaneously. You can have this reaction I drew. Even if a proton is heavier than an electron, it is, right? If the energy of the electrons are very high, then you can have this reaction just happen naturally. It'll happen both directions. It's like chemical equilibrium. And in fact, the rules I had for when we derived the spectrum of a black body, and I said I didn't really care about the table's details, I just said that it can emit photons. This is the same idea. If electrons can spontaneously emit antiprotons and protons, the same exact mathematical framework applies, and you get a spectrum, meaning how many at which energy, kinetic energy, of protons and antiprotons created in this as was for a black body spectrum of light. And so in fact, and remember the energy went like to T to the 4th. So the early universe was in fact a plasma of particles and antiparticles in huge numbers at really high density. And what Dickey and Gamow and maybe a couple of others, but they're the main people, realized is that as that plasma cooled down, all the exotic particles died out, and eventually, in fact, you just simply had protons and electrons. Well, there's another story. What happened to the antimatter? We'll talk about that in a second. Ignore that for a second. At some point, you had a plasma of protons and electrons, basically ionized hydrogen. And eventually, it cooled down so much that you can't even separate electrons from protons, and you formed just molecules or atoms, just unionized atoms of hydrogen. And at that point, before that it was a plasma like a flame. There were photons and electrons and protons all mixing it up. Suddenly there should just be photons left over. And there was the prediction that you should see light from the Big Bang. And then that light, through a general relativistic effect, if the universe is expanding, you actually stretch the wavelength of the light and you lower its energy. It's called gravitational redshift. And this light, which started out as a plasma at around the temperature of 13 eV, the ionization energy of hydrogen, has been cooled down to be very low frequency light. 13 eV is very ultraviolet. It's beyond, you can't see it. We see about 2 eV, 13 eV, not a crazy different energy than visible light, but 5 times higher, right? But that's not what it would be anymore. It's redshifted to where it's a radio wave, or more specifically, it's a microwave. And so that's called the cosmic microwave background. And it was predicted by Dickey at Princeton. It was Gamow first thought of it. Dickey at Princeton realized you could measure it and was trying to measure it. And 2 guys down the road at Bell Labs had tuned a radio telescope up in the cosmos trying to do something else, and they saw some background hum. And they literally thought they had bird shit on their radio antenna, and they went and they scraped it out, and they spent about a year. And then they heard that Dickey down the road had postulated that this was that this existed, and they were realizing they were seeing it. And so just before he could measure it, they published and they got the Nobel Prize. It's a famous story in physics. And so there's and it exactly matches the prediction. I think I said this in the first lecture. That glow of light is the best measured blackbody spectrum, I think, of anything, ever. So just let me see a couple other comments about the Big Bang. What happened to the? I sort of did a switcheroo on you. Yeah.
Since the background radiation was shifted from UV down to microwave, like, was there a time when it was visible?
Sure. Absolutely.
Like, we were able to see it. Like, is there any history of like?
No. The time that shift would have happened, there almost certainly were stars and planets, but it was, one would that have been, it would probably been in the first million years or two, a few million years. It's like that. How does, I'll have to think a minute, but not human timescales. I pulled a little bit of a switcheroo. I first said that you could have this plasma of particles, antiparticles. Then it cooled down to actually just electrons and protons, and that's what gave the light that we see. What was that switcheroo? Well, how did I get from this picture to just having electrons and protons, which were like basically like a very conventional flame? Well, the answer is we don't fully understand. There is a remarkable fact. If you say, well, okay, early on, things must have been very dense, and I had this process going on. There had to have been a huge number of antiprotons, a huge number of protons, a huge number of anti-electrons, huge number of electrons, huge number of antineutrinos, huge number of neutrinos, huge number of muons, huge number of antimuons, blah, 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 all these things, W's and Z's, and all sorts of higher energy stuff, which if we could make an accelerator 1,000 times bigger, we would find out about, okay? Now, the short-lived stuff won't live long, but in a process like that, that doesn't matter. It doesn't have to live long. It's, it's frothing sea. But there is the basic idea, there's the basic idea that as you cool down, eventually the KT will drop below mc squared, say, for the protons. And this process can't happen anymore. These just don't have enough energy to create the protons. KT is less than a GeV. And then this reaction will still happen. These will annihilate away. What we have left over today is 1 part in 10 to the 11th of the total number of protons and antiprotons there were in the early universe. So for some reason that we don't fully understand, there's so many things in physics at this level have turned out to be due to beautiful symmetries. And we would have thought that the laws of physics are such that whatever gave us the Big Bang explosion created matter and antimatter in equal numbers through processes like this. But apparently it didn't. There was a tiny asymmetry between what we call matter and the perfectly valid other form of it, which we call antimatter. It just so happens that there was a part in 10 to the 11th difference between the two. If there hadn't been that part in 11th difference between the two, all that we'd have today is like photons. The universe would just be a glow, period. And, but it's not. So all the weird stuff just decayed away, all the antimatter. And we're left with just, a little bit of, it turns out there's an exact mapping, and this is, the basic interactions preserve this. Turns out lepton number is preserved in all the types of interactions we have. We call it lepton number. It's a fancy way of saying, if you have some electrons, you'll always have some electrons. If I have some process which creates electrons and anti-electrons, I can create an electron and an anti-electron. I give the electron a lepton number 1 and the anti-electron a lepton number -1, so the total number was 0, okay? It's just a fancy way of saying that I can't create out of whole cloth one of these. And I can't create out of whole cloth one of these. And it turns out the number of these and the number of those is exactly in lockstep. So we didn't end up with like a lot of protons and not enough electrons. So we'd have all this charged protons out there in the universe. Nope, turned out we have exactly the same number of protons as electrons. And then of course protons and neutrons formed heavier elements. And now we have everything we've got. But it's all basically electrically neutral. Total charge in the universe is 0 as far as we know. There have been attempts to see if there, for instance, are regions where the universe is antimatter. You know, why not? Suppose the universe, the Big Bang somehow was different. The laws of physics were different in different parts of the universe. If it was some fine tuning of the forces which led to the matter being a part in 10 to the 11th more than the antimatter, maybe that's varying over the universe. Maybe there should be a whole chunk of the universe way over there where everything's antimatter. There should be some no man's land in the middle where everything got annihilated away. And people have looked real seriously for that, and there's no evidence for it. In fact, there's very strong counter evidence that didn't happen. There's lots of speculation that out beyond the edge of the universe, the laws of physics maybe vary. I mean, does this go on truly to infinity? And what's the meaning of infinity? It's something like that. 12 billion light years is already such an incomprehensibly large distance. But fine, let's go out a factor of a Google times further. You know, what's over there? And people speculate based on general relativity and quantum mechanics, you know, what might happen, but you just can't know. So I think I can stop here, unless there's any other questions about this stuff. You know, my basic, I'll say one last thing, my basic research is looking for dark matter, which is we think a form of matter left over from the Big Bang that we know exists, we don't know what it is, that's the dominant form of matter. There's more of it than there is normal baryons made of up and down quarks. And we look for it with normal particle physics type detectors as being in through our galaxy. Anyway, so I've enjoyed the class. Exam on Wednesday, review tonight at 8. Okay, I'll be gone after tonight. But you can see Pete Kiernan with questions. I will be around tomorrow until around noon. And no class on Friday. Yeah.